Hello, and welcome to one of these labs. So we're going to be discussing the motion in one dimension. And so this is just traveling along a straight line. And what we're going to be doing is we're going to be using this software called Pascal Capstone to capture and graph the data that we will be acquiring during this section. So we have a motion sensor here that is able to measure our position or our distance away from the sensor with relative accuracy, and we're going to be using a 10 hertz signal, which means we're going to be acquiring data 10 times per second. And so the purpose of this activity is to explore the graphs of motion, so position versus time, as well as velocity versus time. And how we're going to do that is, again, we're going to be capturing our position data, plotting that versus time, and then graphically seeing how that is represented. And so after this, you'll be able to understand the relationship between position and velocity, knowing that velocity is just the rate of change of your position over time. And we're going to try to do some matching where we're going to try to match our position from the motion sensor to a graph that they have already pre-generated. Okay? And cut. Okay, so what we're going to do is we're going to measure my position as a function of time. And so what we're going to try to do is follow this curve here on the screen. We'll show you that in a little bit. And so what we're going to do is we're going to hit record, and it's going to give me 3 seconds to get into position. So at the start, I'm going to be at 0.4 meters away from the sensor, which is going to be about right here. I'm then going to follow this curve as best I can for the next 10 seconds. So I'm going to move, so as the position increases, I need to move back farther away from the sensor. And then as it decreases, I need to move closer to it. And so we're just going to see how this goes. So I'm going to hit record. I can see where I am right now, so I'll get in position. And then I'm going to start moving. And so you can see I kind of went farther away, and then I had to try to compensate to try to get back as much as I can. And so for this, we want to do it a couple different times, and we're trying to get a better match score. And so this is just like the difference between what our positions were times some factor. And so the closer you are to 100, the better your match. So here, it looks like I was pretty fine. But then as we got farther away, I mean, it was harder to actually see what we were doing. So we'll do this a couple different times, and we'll record just a screen this time so you can get a better idea of what it looks like. Okay, so we're going to do a second run. This time we're just going to show the graph. So this blue line was our first run, and this red line is what I'm trying to follow. So we'll do a second run. This time we'll just see the graph, and we can go ahead and start this. So okay, so that was a little better. Slower going back, and that's just because I didn't want to run into a table behind me. And then I started going back a little sooner, and then I overshot where I wanted to go back to. So that's what this part is. So it's just showing that your position over time, we can easily measure that. And I have a decent match score of 86. But yeah. So after that, okay, so we can just describe what our ideal motion would be. So try to figure out how to better match the score if you were here and stuff like that. So we'll cut here. Okay, so we're going to be starting again. We have our velocity versus time graph. Again, we ran into an issue with our auto scaling, so we have it set up in a way that now we're not going to have that issue. So we'll start again. So we'll hit a go. And we're going to stop that here now again. Stop. So we're going to auto scale. Top left there. And we're going to go one more time. Hit record. So that was much harder than I had anticipated. Because I'm trying to follow it as a position graph as opposed to a velocity graph.
Okay, so the goal of this experiment is to measure your velocity and try to match the velocity time graph that's already provided in the software. So the way it's done is that the person doing the experiment will move to and from the center and the sensor will record their velocity versus time and compare it with this graph. So you're supposed to try your best to match this, and there will be a max score that will come available here. And notice that this is a velocity time graph, so a linear slope means you have to accelerate. So the way is that you start, you accelerate, then you stop accelerating, and then you decelerate, and then you rest, and then you accelerate again, and suddenly decelerate, and so on and so forth, and try to match the curve. So the data recording, you have to press record when you're ready, and then move accordingly to match this curve, and you have to repeat it at least twice or thrice and find the best score that you can make. And the recording will automatically stop on after 10 seconds. So let's see how the recording looks like.
And this only works with the manual, with the lab manual.
Score of 92. So this is
Wow.
this is what you should aim for. It's a score of 92, and it's pretty close to the curve that's provided. Okay, so after this part, after you have managed your best score, you're supposed to move on to the file and answer the remaining questions. The next page, you're supposed to record your best matches, like which round gave you the best scores in the previous experiment that we just talked about. And then you're supposed to describe your ideal motion, like how you moved during the previous experiment to reproduce the curve as closely as possible. So like you have to say that you move backward at constant velocity or increasing velocity. So you have to mention whether you accelerated or decelerated like that. So for example, in this part you accelerated uniformly, so you're supposed to mention that here along with the other, and do it for the rest of the curve as well. And that's the next page. Page 13. So going on to page 14, you have to answer the question where they ask that what are some real life situations where graphing the position or velocity of an object would be useful. So there are various examples. One example could be that when a speedometer is recording the velocity of the car, if it draws the position time graph, the slope will give the velocity, etc., etc. And then to move on, the next page just describes that you have to, in this page, you just have to, it describes what this curve actually signifies. So it's a position time graph, unlike the last one, which was the velocity time graph. So this straight line here, it means that the person moving is moving with constant velocity and not accelerating. And from this graph, we are supposed to calculate, answer the questions. So you have to calculate the average velocity and then verify and just compare the average velocity for the two parts that you compute to the different methods that you use to compute it. And then we have the last page where you just record the answers of part A and part B here. And you're supposed to show at least some of your work and not just the answer. And that's it for part A. Okay, so this is part B of the experiment where we will start from page 5 of the file. So here on page 5 we first have to answer 3 questions, like what is the shape of a position versus time graph of an object with uniform acceleration, what is the shape of a velocity versus time graph of an object with uniform acceleration, and how to determine an object acceleration from the graph of velocity versus time. So to answer these 3 questions, and you're supposed to answer them from the theory discussion that was there in the first part of the video, and that should cover all of these. And then moving on to page 6. So page 6 just gives you the background or the set of equations that we will be using for this lab. So these are the equations of motion in one direction. So, and hopefully they are also explained in the first part of the video. And then on page 7, it describes what to do. So basically, we will be dropping a basketball, and the sensor, and we know that anything that is falling under the Earth's gravity is moving with constant acceleration, and the sensor will record the position versus time and velocity versus time graph of the ball. So yeah, so here we are supposed to drop the ball, and the sensor will record the graphs automatically. So you just have to press record before you start, and then once the graphs are there, we will be fitting the graphs with straight lines for velocity and parabolas for position, and then from that we will determine the acceleration. Yeah. So in this part, we're supposed to drop the basketball from the sensor, and before we do, we have to set the sensor to object setting. It was on human setting for the part A, and that has to do with something about the sensitivity of the sensor. But yeah, so after setting it to object, hold the basketball as high as possible, just below the center, click record and drop it. So, you ready?
Yep.
Go.
Oh no.
Ready? Okay.
So what do you have there?
So we have the position and velocity graphs recorded by the center. As you can see, that the position versus time graph is a parabola, which is what we expect for a uniform acceleration. And so we see multiple parabolas because the ball is falling, then bouncing, then going up again. So when this is where the experiment starts. So the ball is uniformly accelerating, then it hits the ground, the direction of its velocity is reversed. So now the position is decreasing, and the velocity is also decreasing because the acceleration is in the opposite direction. And this is the maximum height the ball reaches after it bounces off. And then it again starts to fall, accelerating uniformly towards the ground, hits the ground here, and then changes direction, and then repeats the entire process. And each time the height reached is smaller because there is some of the energy that is lost during the collision of the ball and the floor. So the parabolas get smaller and smaller and smaller until the ball comes to rest. And similarly, if you look at the velocity time graph, when we drop the ball first, it's accelerating uniformly, so we get a straight line for the velocity time graph. This is where it hits the bottom, and the velocity changes direction almost instantaneously. So there is a sharp fall from here to here, and then the velocity, then the ball rises again and then falls and then hits the ground again here and so on and so forth. Just like the acceleration, just like the position versus time graph, the velocity versus time graph also gets smaller and smaller for the same reason until the ball stops. So yeah, back to the velocity time graph. So just similar to the position time graph, the velocity time graph also represents a sort of periodic shape. So this is where the ball starts falling and the velocity is increasing because it's accelerating uniformly, and this is where it hits the ground and the velocity changes direction. And then when the ball is going up like this, the velocity is actually, or the magnitude of the velocity is decreasing, but it looks as though it's increasing because the sign is negative here. So it goes to 0. This is the maximum height the ball reaches after bouncing from the floor, and then it again starts falling and accelerating. So we again have a uniform acceleration here when it hits the ground again, and so on and so forth. So, and just like the position time graph, the velocity time graph is also getting smaller and smaller because of the same reason until the ball stops here. So now now that we have the graphs, we can repeat the experiment a few more times before we actually fit the data to get our measurements. So let's repeat it one more time. So, you ready? Okay, so that was not specifically drawn. So should we delete it and try again?
Yeah.
So now we see that so the second graph is almost exactly on top of the first one. So same here. So if you drop it from the same height, you should get, and start at the same point of time, you should get the same graph.
Can we do one that you drop it from a lower
Yeah, so
height?
let's see what the graph looks like when we drop it from a different height. So it's still at 6 seconds, so I'm going to change this. Ready?
Yep.
Try once more. Do delete last recording.
Good.
Yeah.
So as we see that because it was dropped from a different height, the origin of the graph has shifted, and so it resembles a very, very similar shape, but it's shifted. So now we have done the experiment 2 or 3 times and saw that we get the same shape regardless, and how the graph actually relates to at what height you are dropping from and at what time you are dropping after pressing record. So now we can choose any on one of these 3 sets and fit the data with the curves that we know, and then record the constants that the fit returns. So yeah, could you take a break? Okay, so now I have selected my best runs that I'm going to use to fit the data and find acceleration due to gravity. So the first thing we need to do is zoom in and position the graph properly so that we can fit it. And now the next thing we need to do is select the set of data points for which we want to sit. As I said, that we want to fit. As I said before, we have many parabolas because the ball is bouncing off and on and off again from the floor. So we have to choose only one parabola to fit, because a set of parabolas is not one parabola, so you cannot fit one parabola on a set of parabolas. So let us select this parabola, for example, So so to select that, we need to click on this button here. So which says if you so it's the fourth button from the left, and if you put your mouse on it, it will say that highlight the range of points in active data. So just click on it, we will have, and the highlighter will be here. So a box will appear on the screen. So we have to move the box and change its size so as to include only the data points that we want. So let's choose this parabola and change the size of the box. So more or less only this parabola is now highlighted, and now we can fit. So to fit, we just click on the seventh button from the left. So there's a drop down menu. If we click on it, the function it will give a menu of functions that we can fit on the data. But we know that the data will be parabola or rather quadratic, so it will fit something like y equals ax squared plus bx plus c. And if we click on that, it will give us the fit. So the fit is not visible because, yeah, it's visible, it's the yellow line. So you can see that it lies almost exactly on the points. And so this is the function that was fitted, and after fitting, we get the values of a, b, and c. So c is basically the height at which we are starting from. So at t equals 0, we have a certain height, so that's our c. And b similarly gives the slope of the graph, and it has also to depend on. It also depends on at what height we start the ball from, or what was the velocity of the ball at the time of the start. And so, but the constant of importance here is a. So a is just half g. That comes from our equations of motions. That there is a half gt squared term in our equation, and so a is half of g, which is this, and so g, the acceleration due to gravity g, is just 2 times this. So it should, so it's very close to 9.1, 9.8. And so it should be something like 9.66 here, which is reasonably close.
4.66.
Yeah. So let's do the same for the velocity time graph. So let us highlight our data point. So which is the same way we select the fourth button from the left where the box appears. Okay, now so we can do the same thing for the velocity time graph, except we will be fitting a line instead of a parabola, or instead of a quadratic. So after this fit is done, we have to just click on the velocity time graph and then select the highlighter again, which is again the fourth button from the left, and another box will appear. We'll again have to position our box so that it includes the selected range of data points. So let us choose this line, the set of points in this line, and let us try to fit a straight line here. So we again click on the fit button and choose linear fit this time, and not proportional because we have an intercept. So let us just choose linear, and as you can see, it has fitted a straight line on the points, which is the line of best fit. And you have the two constants. So this is the function that we fitted, x equals mt plus b. M is the slope, which is equal to the acceleration due to gravity, which it measures to be 9.66, and b is just the velocity at time equals 0. So since we chose only this graph, so it is choosing time equal to 0 to be this point, and which is the velocity of the ball at this point of time. So it's during the first bounce, right after the first bounce. And then we can do the fit. So to measure the acceleration due to gravity from both these curves, and we have our constants. So now we can move on to the next pages of the file and complete and answer the remaining questions. So here, the next page, which is page 9, you have to answer these questions. So about the shapes of the graphs, and you can just look at the graphs before on the left side and count and compare the shapes and write about them. So about the parabolic position time graph and the linear velocity time graph, and then you have to say how well your predictions matched with the plots generated by the motion sensors, and by predictions we mean the values we get by using the equations of motion. Then moving on to page 10, we are required to answer more questions. So what were the variables in the activity, and by variables we mean that what were the things that could be varied. For example, the height of the ball and the time at which we start and stop recording and stuff like that. And then we're supposed to answer the next question, which asks what other variables could be tested and what is our hypothesis of the result of this, of testing these new variables. So we can also measure other quantities using this, like momentum and stuff, so where you just multiply the velocity with mass. And then moving on to page 11, so we're going to do another experiment where we find the acceleration from the position time graph, which is kind of like what we did when we did the quadratic fit. So, okay, so now we're the fit that I showed how to do on the last pages. You're just gonna have to do them separately. Here, it explains the same thing that I just did a few minutes ago, and you have to just fit it here. So you can fit the two graphs separately and write your constants here. And then similarly for the velocity graph. So, and then moving on. So here we have to answer more questions. So we have to from the constants we fitted out from the previous pages, we have to write the constants here. So this A is just the A we obtained from the quadratic fit. So that's just 2 times. We have to write 2 times A here, which was 9.66 from the fit. And then we have to also put the slope of the velocity time graph, and then using the acceleration that we compute from the fit, we have to answer this question, which asks that under the same acceleration, what time would be required for the ball to fall 50 meters. So the equations of motion are given. So it's we will use this equation, this particular equation for our experiment, and so we know x, which is 50 meters, and then if we are dropping it from rest, v naught will be 0, a is just 9.8, and we have to solve for t. So that's the answer here. The answer of this question goes here. And then using that time, we have to calculate the speed of the ball when it reaches 50 meters from its dropping point, and we just use this. So if we are dropping it from rest, v naught will be 0, so v is just a times t, and a is the acceleration that we calculated here. Okay. So the next part requires us to compute the percentage difference between the two accelerations that we got. One from the position time graph and one for the velocity time graph. So we have to write the values of the two accelerations. They will appear here. And then we have to calculate the percentage difference using this formula that's given. So we just subtract the two accelerations take the ratio of that with one of the accelerations and just multiply it with 100%. Notice that there is an absolute value sign over here, which means that whichever value we subtract from the other, we only take the positive value. So even if the difference is negative, it doesn't matter which value is higher or which value is smaller. So we ignore the sign and take the 100% and calculate that and write it here. Then moving on to the next page, there are some more questions we need to answer. So the first question on this page 17 is, in this exploration you used a graphical representation to show how the position and velocity are related for an object with constant acceleration. What did you discover? So just you have to look at the graphs and answer what you discovered about ball falling under uniform acceleration, and then you have to write about what were the sources of error in the experiment. You can say that, you know, the sensor, there is a limitation or least count of the sensor. Then there could be things like when the ball is dropping, might have already have some velocity, but answers like human error are not acceptable, and you will lose points if you write those. And then moving on to the last page. So you are required to answer these last two questions. So the first one is, what are some examples where the equations of motions are used? So you have to think about daily life situations where you can use the equations of motion to measure something or maybe to make our life easier. And then the last question is a problem. So it said that a hot air balloon is rising up with a constant speed of 3.75 meters per second. When the balloon is 7.5 meters around, the balloon drops its compass. How much time elapses before the compass hits the ground? So first you have to so we have a classic 1D motion problem. So we have to use the equations of motion. So it's given that the speed of the balloon when the compass is dropped is this. So this is our v naught, and then we have our height. So this is x. So we use our equation x equals v naught plus half gt square. We know the value of g, we know the value of x, and we know the value of v naught, and we have to just solve for t. And the important thing to notice with this one is that this velocity and g have opposite directions. So you can either take this to be negative, g to be positive, or vice versa. Don't add it. So don't add this velocity to the half gt square, you have to subtract it from it.